I'm sorry for the noise around me, and let me just continue with it like this. My name is Abraham Thiong Ajak Thiong, and I'm going to make a short presentation about my topic. Actually, I'm solving a short shoot defects in injection molding using Taguchi method and AI5 frames combined with Python-based computational modeling. So I'm just going straight to the point. I'm not going to read the abstract because the PDF will be uploaded later, and if anyone want to read it, you'll find it there. Actually, I, the author, I would like to comply with the I5 evaluation criteria such as possible. And here is the photo. We have deep awareness, intention, nature thinking, idealizations, and instruction. So our awareness in this problem is I'm finding what caused the short shoot, because we all know that short shoot is caused incomplete filling and product failure. The high defect rates increase in production costs and rework. And our intention is also my intention is to improve injection molding quality, is to establish repeatable data-driven process, and to eliminate the shortage through computational optimization. And here in the background here, so injection molding is one of the most widely used in manufacturing process for producing high volume plastic component with consistent quality. So in this process, it involves a lot of material, main materials and injection molding. And that I'm not going to read all of it. I'm just going to take you through the I5 process and how it is important to use it. So here is initial thinking. In initial thinking, we identify the influential factors and possible root cause. So the root cause, I've selected three parameters as the root cause of the defect. One is nozzle temperature that affects the metal viscosity. The injection pressure determine the cavity filling capability. Injection molding time influence the continuity and packaging. So in initial thinking, we also assess the data is required, all the tools that are needed, what are the assumptions set. So before we solve the problem, we need to decompose the problem such that it will be easy for us to solve it. In problem decomposition, we have decomposed the problem into three profile combinations, and these are the parameters: nozzle temperature, injection pressure, injection time. So despite the operator experience, there is insufficient structured data analysis identifying optimal machine setting. So we need a systematic, repeatable, and computational method to identify the most critical factors influencing the defects, and also determine the optimal operating conditions. So, and also reduce the waste and improve the time cycle performance. And so after we decompose the problem, we need to see the construction of the parameter principle. So as we have identified the key injection molding parameters affecting the short shoot, and the L16 is applied orthogonal ray that I've mentioned that we are going to use Taguchi. In Taguchi, we use L16 experimental design to make a trial to see if there's going to be a short shoot or not. So in conceptual analysis and side arc, so we have the modern state of arc approach. We also have the approach where we design experimental design, EDO, robust design, and integration. We also see the ANOVA later. And also in this part, we are going to use the methodological part, which is idealizations. So the methodology combine the experimental design, statistical analysis, and computational modeling. So here, this is where we're going to determine or determinations of optimal parameter in combination, and then select the factors, three factors later. I've already mentioned that things. So let's continue. Okay. So these are the parameters that I've selected with four levels because nozzle temperature, we have level one, level two, and level four. Within all these levels, we have to try it on the machine. You see, like in level one, we have the temperature is 215, level two, 223. So we put all this data on the machine, working on the injection molding machine and see the result. Is there a short shoot? So we tried it 4 times to see if there is short shoot or not. And then later we'll come up with the conclusion. So these are also the control variables. We have injection speed, back pressure. So these are so within the injection, within the Taguchi method, there is what we call L16, which is orthogonal rays. So this L16, we use L16 because it is minimized the resources, so it is cheap. So this is the result. And after we run the result 4 times, this is what we get. So within this first trial, we get 0 short shoot up to the other current, we got some short shoot. So after we got the short shoot, we calculate the average. After we calculate the average here, so this is the average of 4 runs. So after we calculate the average, then we see the computational thinking. So what do we do? What the computational thinking and underprints entire projects by enabling the data structure and processing. So what are we going to do? The algorithm calculation. So statistical computation, predictive model. So by applying computational thinking, the project decision from experimental observation to predict and optimize driven manufacturing, reinforcing the roles of computation in modern engineering problem solving. So the algorithm for data processing and analysis. The first algorithm is the short shoot defect calculation. So after we all make trials, so now we are going to calculate the short shoot defect because in the molds cavity in the molds there are 24 cavities and the number of short shoot effect in within the 24 cavity there's number of the defects minus the number of product in one mold, so divided by 24. So this is exactly what we're gonna get. So like there's 20 affected and 24 times 100. So this is what we get. So the second one is the Taguchi S ratio like the better. So we find the average short shoot defect by each round. So and this is how it is calculated. And this is the result when you run it using Minitab, which is still fall under Taguchi. So this is all what you get. So the third algorithm is a Python simulation or Python pipeline. So experimental database which is run 16th, which run 16th, 3 factors by 4 replication. And then after that, after you run it, you model the regressional model or predictive model. So after that, you load the data into Python pandas, then you compute the average. And this is what you got when you model it across. See. So let's go. Algorithm 5 is determining the optimal setting. After you run all the things that are made a 4 trial and you run everything, you use Taguchi and analyze them, then you see the optimal Taguchi setting here. Like you see on the graph, like the input is the responsible tables and the data runs because the table are already here there. You also divide the hash label for each factor. So this is the nozzle temperature, the optimal setting of the parameter that I've set. Within this, if you input this, put if you put this another input in the on the machine, you'll get zero short shoot. So now let's look at the Shaddai prime frame. So you understand the problem of the short shoot. So this is Shadia. So when we understand the problem or the short shoot, what is really the problem? We get the problem. I think it's very simple to solve it. Like we understand the real impact of the short shoot on the product, and we set the goal how to solve it. There are many methods you can use to solve it, and also identifying the parameters. What are the parameters that are affecting this? And this is why I always selected three parameters to solve, to see and solve the problem. Also build the idealization, we build a Taguchi and Python model, and instruction run the experiment evaluation. So this is a flow chart. So our goal is to minimize the short or reduce the short. So when the short is not reduced, then we go back to another analyze the identity the cost. So in the instruction, these are the instructions when we want to see if execute the stage of Chadai 5 frame where analytical planning and IDS modeling are transformed into concrete experiment computational decision making. So these are the steps that you follow: preparing the injection molding machines. Then you select the material that you want to use. Then you fix the control variables here. Then you set the control factors. Also, then you run the complete cycle. Then you repeat each experiment each time. You record them 16 times. So these are the results. So after that, the short defect result. So this result was measured 16 experimental time using the application. So the average is here, and the post. So in the first round there is 4, the second round 0, no, no. Then we calculate the average. So in this, so it, so in what has been shown in this main effect plot. So the parameter that is the most influential factor is injection pressure. The second is, and the second is sorry for interruption. So, and the second is the nozzle temperature. So this is the graph. This is the graph. So in this graph shows that this graph shows that the process influence the main factor R in manufacturing at the low temperature between 215 to 225. So the defect rates are maintained stable at 15 to 225. But if it is above 30 or rise, that indicate the excess heat increase the defect. So that is according to that graph. The same here, the defect rate remain relatively stable between 215 to 225. And when it rate to 30, it causes excess heat. So that means the common in optimal condition from the main effect. So the optimal setting should be the optimal setting should be 220 to 225. So this is the and the ratio it should be 50. Okay, that is it, and this is the discussion. So let's take a look at the code on my code. So this is my code. So this is the code. So this is the code. So when I run it, it works. This is how it works. Get some result here.